Okay. So, okay. Okay, welcome everybody from home. As usual, please feel free to ask questions if needed during the lecture. We have already one question today. So today, the lecture is going to be devoted to understanding a bit more about convolutional neural networks and see how to train them in particular, and to have a look at few successful models that have been proposed in the literature. So, please, there was already a question. Okay. Maybe it's better if maybe I can draw at the whiteboard. So the question is about how the filters in a convolutional layers are arranged. Yeah. So the first layer, this is the image, right? 32 by 32 by 3. And now we set a convolutional layer at the beginning of this network to process this image. So everything has to be considered as a volume. Okay. Now I take a convolutional layer here, which has like which has 3 by 3 filters. Maybe I should start recording. Okay, but just as I finish answering the question, I will start recording. You remember me, okay? So 3 by 3, and they have 3 filters, okay? Now, okay, no, don't say 3 by 3. Let's say 3 by 3 but 5, just not to confuse too much. And now each filter here, each of these filters should be able to take as input the image. And to take as input the image, when you do convolution, the filter has to slide only spatially. This for respect to whatever volume you have. So your filter is going to be, each filter is going to be 3 by 3 as we design them, but that wouldn't be possible to make convolution against the input. So the filter has to be itself 3 by 3 by 3. It has to have 3 slices. Sì, il conteggio. Prego. Prego, 3 by 3 by 3. Okay? And now, if you have 5, okay, the convolution of this image against this will give you just one slice in the output. Because in each pixel, say 7 and 5, this means that you take this filter, you overlap to this region, which is, okay, 7th coordinate and 5, and then you overlap the red channel to the first layer, to the second, and to the third. You compute the product element-wise. Then you taking these as the weights and these as the inputs, you sum them all and you get a number. The sum is made over all the 3 channels. And now you have 5 of these. So you will have 5 slices in the output. Now, if you want to take another convolutional layer here, take another convolutional layer, which is, I don't know, 3 by 3, 27 filters. Each filter here needs to be like 3 by 3 by 5, because otherwise you cannot compute the convolution. Is everything clear to everybody? Any question? Any other question? No? Okay. So, indeed, instead of starting from these, I can start from another, just mentioning briefly how to do this stuff in Keras, which is at the bottom of the last presentation. I mean, this is good just to summarize, yeah? Just to summarize the most relevant techniques, okay? The most relevant aspects of how to compute the convolution arithmetic and how to implement convolutional neural networks. Okay, you are familiar with Keras because you have been using already with Francesco Lattai, right? So there's no point of talking about Keras, but now okay, so I'm starting recording and I'm demeeting a few guys that have not been logged in. Okay, perfect. So, again, if there is any question from home, okay, yes, the registration. Now, please directly ask. Okay, so what you will be handling now in Keras, everything will be considered as a 4-dimensional tensor. It's not going to be a matrix, it's not going to be like a volume, but it's called 4-dimensional tensor. And the reason is that because when you train a network, you're going to feed like a batch of images. Okay? So I think it's kind of organized for that purpose, to take as input a batch of images. And batches of images, let me check just the webcam, sorry. Can you, the webcam, can you see me? Ah, okay, I found how to remove this stuff. Okay, cool. But from home you can see just the whiteboard, right? You cannot see me. It's okay as long as you can see the whiteboard, the blackboard. So everything is organized in a 4-dimensional array.
Professor, the blackboard is very zoomed in.
Yeah. Let's say Lavagna. Is this better now?
Yes.
Okay, let's keep this. And now it depends on what's behind your Keras. If there is TensorFlow, typically the first dimension is meant for keeping track of the sample. Say if you got a batch of 20 images, the first dimension is meant to as an index for the images in the batch. Then you got the height, the width, and the channels of your image, of your model. Okay? And now the way convolutional neural networks can be assembled in Keras is very simple because you just have to import a few modules. We see sequential. So sequentially is the object we should initialize in order to create a convolutional neural network, because it's a network that is kind of processing the input sequentially, and And then here you see all the layers we need in order to implement those network that we have already seen last week, like the simplest network ever, okay, which is made of convolutions and max pooling and finally fully connected layers. So in Keras are called dense, and the others are very, their naming is very straightforward. Bear in mind that you need also this flattened layer as soon as you feed your network from when you quit, when you get to the deepest layers. Was unmuted? Now it should be okay. Maybe I unmuted by mistake myself. Okay. So you have multiple layers, okay? And then you just, once you have initialized your model sequential, but this is probably the same as before neural networks, right? Once you have initialized your model, you just add layers to the add method, the model. And here you can see how these are defined. In the conv2 layer, in conv2D layer, you have to specify a few inputs, which is the number of filters, the size of the kernel, which is assumed to be squared with just one number, the type of activation. So you don't need to feed in any there is no layer for the activation. It is just an argument for each and every convolutional layer. So you cannot place a convolutional layer without any activation. And then you see here I'm adding just a simple convolutional layer, which brings my image to a 64 channel. And then I'm taking a max pooling, which is halving the spatial extent. And then I'm flattening everything. And then I'm placing a fully connected layer, which has 10 outputs. Can you see now this from the notation in Keras? And you need to specify the input shape for the very first image. Then you don't, because the input of stack multiple convolutional layers, then the input is going to be, the input size is going to be the size of the output of the previous layer. Okay? I leave you these to let you read the documentation if you need any further information. But you think you can play with this now. I mean, it's very straightforward. You can prepare your network like stacking, as we've seen, like in LeNet, multiple convolutional layers with their activation, max pooling, convolutional max pooling, convolutional max pooling, and then finally flattening and then density. At the end, you can see the model summary as for feed-forward neural network, which is telling you what this network is made of. In this case, there is just a convolutional. The max pooling, for some reason, was not reported. So probably I took this screenshot like not referring to the previous image. For training, this is like other neural networks. You just need to compile the model, and when you compile the model, you set what kind of loss and what kind of optimizer for the gradient descent and what kind of accuracy to display and to measure. And then once you have compiled the model, you actually run the training by the fit method. Okay? So is this everything familiar to you, right? Or not? Please give me a feedback. It's okay. And have you seen the callbacks and other options? So these are the options that can be used in order to better control the training phase. For example, you can introduce a list of callbacks, which are a set of functions that are being applied at each stage of the training process, say after each epoch, for example. And these have a look at the state of the internal training and perform some action. One action can be early stopping. So you can stop your training when the validation performance stop decreasing, while the training instead, training performance continue to decrease. Or you can store a few checkpoints. So these are very useful. If your network takes a few days for training, it would be good to dump the model after each epoch, such that if after few days you, for some reason, you lose the connection, everything falls. Or if you're using like Colab or Kaggle machines for training your model, then you got a limited time every day. So it's good to save checkpoints. So the model is being saved. Then you can load it. So the model is being saved, say, after each and every epoch. And then you can restore your model and continue the training since you stopped. And you can have the callbacks for saving checkpoints or as early stopping criteria, like on the validation loss, as I was saying. And then, okay, you got already the method, a method for testing, but this should be the same as for other advanced learning. Okay. Now, let's move further. Few comments on how are organized convolutional neural networks. And the idea is that I want to draw a parallel now between the convolutional neural networks and the feed-forward neural networks. Because indeed, convolution is a linear operation. So some of you guys were asking, how is it possible that a convolutional neural network provides features that are meaningful for understanding the content of the image, right? But indeed, this is exactly the same. The mechanism is exactly the same as a feed-forward neural network. You are computing a linear combination of the inputs, and then but with these weights that are being, say, learned, and then you're computing, you're performing some nonlinearity. So at the end, it's concatenation of these. I think it's a concatenation of nonlinearities and linear combinations with learned weights. Okay? So if this works for a convolutional neural network, so if this works for a feed-forward neural network, this can work also for a convolutional neural network, but then what is the difference? So if I were to draw now my convolutional neural network, so this is the input, let's take, let's take a single channel to make things easier and take a single neuron. So this is my image, right? And I have a single filter. Yeah, I can drop perspective and can just take orthogonal projection when drawing. Maybe it's simpler, right? Yeah. So this is the image. This is my convolution. This is the learned filter. Let's call it W. And the result is going to be an image having the same size. Correct? Okay, same size. Maybe it is not. Now it is 4 by 4. This can be seen as an input. This is the input of the neural network. It can be seen as an input layer of a feed-forward neural network, right? right? So these are 16 guys, okay? So I'm expecting a column of 16 input neurons. And I'm having in the output 16 output neurons, correct? So this guy is exactly this guy. I can draw an arrow. So the number that will be here in the output, the activation that will be here in this slice, the output volume of a convolutional layer, it's now reorganized as a feed-forward neural network and will be here. Okay? And of course, the input, so this is going to be the first pixel, this is going to be the second, say first, second, third, fourth, so on. So these are the input, 1, 2, 3, 4, whatever. Okay? So I can unroll completely my input and my output, and I can look at this as a feed-forward neural network, correct? Correct? Now, if this feed-forward neural network were a traditional feed-forward neural network as the one you've seen, how many connections should you have here? This is 16. This is 16. What we should have, if these settings, 16 times 16 plus 16 connections, because this is a fully connected neural network, the one you've been studying so far, right? Now, okay, this is a super simple convolutional neural network, but I mean, then if you add multiple layers, you can do the same. You got more neurons in the input, more neurons in the output. Well, actually, for each one filter, it's only one layer in the output, so the number of output neurons doesn't increase. Correct? So, but now, what can it? What is the? What happens instead when I have a convolutional neural network? How many parameters do I have here? 9 plus 1, the bias. So it's, I mean, this is incredibly more, right? So this is 256 plus 16. So it's incredibly more weights. And this is something we already seen. But what does it mean? So this means that here I have fewer weights. But let's have a look first at what are the connections. And by connection, I mean which pixel in the input contributes to define this output neuron. So which pixel in the input, or which value in the input, which activation in the input layer contributes to define this output value. So I'm placing the arrow here, okay? And now I'm drawing what are the pixels that are contributing to define that output. And if the filter is 3 by 3, there are only these guys contributing, correct? Yeah, no, I'm talking about the inputs. Which inputs are contributing to define the output here? Then they use these weights plus the bias. But the input, now I'm talking about what are the, so I'm definitely talking about what are the connections between this guy and the input. Now you can see that instead of having 16, you are having only 9, right? But this because the image was very small. So say I give you an image which is 200 by 200. In the fully connected layer, here I would have 4K, right? And each pixel, in each neuron in the output will be connected with 4K values, okay? Now, in a fully connected neural network. If I take a convolutional neural network, nothing changes. What influences this output? It's only these 9 pixels in the input. And they are 9 because the filter is 3 by 3. So you can see that there are sparse connectivity. So while any fully connected layer would give you connections between all the input neurons and each and every input neuron and each and every output neurons, which means that to define this activation, all the inputs contribute. In a fully connected neural net, in a convolutional neural network, only a few of them indeed contribute. Is everything clear to everybody? Okay? Sorry, guys. So here only 9 non-zero connections there are. There are only 9 non-zero connections. Sparse connectivity. But this is not the only, because if each output neuron would have like 9 weights plus the bias, I would have now, since I have 4K or 16 or whatever of neurons in the output, I would have like these times the number of neurons in the output. But this is not the case, because you know that here, the parameters I have in this layer are only 9 plus 1, not 9 plus 1 times the number of output neurons. Correct? And why? So what happens to these weights? No, there's no that. It's one image, one layer gives you one layer in the output, one field, one field. So what happens? Why here I have just like 9 plus 1 weights, and here I told you, okay, let's move these to a fully draw it as a fully connected, say as a standard multi-layer perceptron, and draw the connection. We have seen that there are only few connections between each input layer and each output layer, correct? But then, and this gives us the sparse connectivity, because what contributes to this output are only a few pixels in the input that are nearby that, correct? But then if I take this, another pixel, okay, this is not included. If I take this, say, which is here, I should have other values influencing them. So there should be other 9 plus 1 weights. So here the number of parameters should be 9 plus 1 times the size of the output neurons. But we know that this, you see, there is a mismatch. There is a mismatch which is this times n. Here in a convolutional layer, we have just 10 parameters. Here, if I'm drawing just sparse connectivity in a feed-forward neural network, I would have n times more, where n is the output, the size of the output layer. So what's the difference? Okay. So from home, someone want to say something from home?
Yes, so basically the weights are kind of shared by different input neurons. It's not a one-to-one mapping. You have some different mappings between input and output that have the same weight.
Okay, so it's very disturbed the audio here, but I think you got the point, and you mentioned the correct word, which is the weights are shared, which means that these weights, like W, let's call them W1, W2, W3, are used the same to compute any other output neuron. So I'm here, I'm taking the output, this output layer, so sorry, in this output neuron, he will have his own sparse connectivity, but the weights are going to be the same. And I mean, this is why convolutional neural network has so little, so the convolutional layers has so little parameters with respect to feed-forward neural networks, because sparse connectivity, you don't have dense connectivity. If you look at this as a feed-forward neural network, each output neuron is connected just to a few input neurons. And the weights associated to this connection are the same for each output neuron. Now, taking another filter would be to have another output, which means to increase the output size. But this is, nothing changes. In the other part of the output size, there will be connections with the inputs, which will be always sparse with shared weights. I don't know what kind of noise is this. Okay? And this is actually what is written here in the slides. But the illustration here is one-dimensional, so you might miss this. I think we can jump directly to the next. Okay, but this is, I mean, a good, so it is important to stress why you have like shared connectivity. Say, it doesn't make much sense in a feed-forward neural network, traditional, to use like shared weights or sparse connectivity even as well. So if you want to compute like regression over a number of input features, which are like the size of a given product. So here you got a lot of measures. And say you want to classify these as whether it is faulty or okay. I mean, there is no reason when you design your feature not to take them all into considerations, right? You have been producing some kind of product, and you have been taking kind of 20 measures out of this to check whether it conforms or not to a reference standard. You might want to check them all, right? Instead, in convolutional neural networks, you are handling images. Images are very redundant. You remember what we were saying. And what you expect is that the output, and there is locality, right? So the value here might not be very influenced by pixels too far. So to understand what's there nearby this location in the image, I don't need to take the whole image. Now I have to take a small portion. And then, in these settings, doesn't make any sense to use shared weights. So if I use certain weights to compute the first feature, there is no point of using the same weights to compute the second feature. So in this case, it will be even the same. If you use full connectivity, if you're not using sparse connectivity, it doesn't make any sense to use share weight, because otherwise it would have always the same value. But indeed, in the image, it makes perfectly sense to use shared weights, because these filters can be seen as kind of detecting patterns, finding out some peculiar structure in the image. And these need to be computed everywhere in the image. Need to be computed the same through the whole image. Okay? So it's not just a matter of reducing dimensionality that they came up with this convolutional neural network, and it's not just by chance that this convolutional neural network, they work. It is because, due to the nature of the input image, which has a spatial resolution, with the spatial dimension as a very substantial meaning, that the network has to be done like this. Not take the whole input to define an output and use the same weights to all the image, because some relevant pattern can be local and can be found everywhere in the image. Okay? So far so good? Any question? No? When you say okay, only Google replies. So it's quite disappointing. Oh, there's a question, perfect. So the CNN can be applied to any kind of image where these properties are meaningful. In an image, they are. If you tell me, like, take one row in a table, in a database, I wouldn't say this is relevant. I wouldn't like to extract features that preserve like the spatial coherence, say tabular data that are nearby need to be jointly considered and not to consider those that are far away, and not to use the same weights to all the tabular data. But if you tell me like a signal, like an ECG signal, is kind of like this, then, I mean, and you can get this signal, and then you can get another one, for example, the spike is slightly displaced, then it makes perfectly sense to use a one-dimensional convolutional neural network. Because what would be meaningful in order to interpret this signal is their pattern. It's its own pattern, sorry. So, and for example, it doesn't make any sense to have like a fixed input like it would be if we take a fully convolutional neural network, a fully connected neural network, because you would be always looking, say, at the pixel number, at the sample number 103, and in some case it is the peak, in some other it is not. So it would be much better to have your filter to learn some patterns and use these kind of weights to detect those patterns that are through all the signal, through all the domain. So when you are observing signals, images, videos, audio signals as well, definitely yes. So for example, if there is an arbitrary displacement in the input, of course you have to go for this. You see some very redundant nature in the input, and some kind of pattern that really identifies what would be the output class, then go for convolutional neural. Please. Sure. Say, take a feed-forward, take a fully connected feed-forward neural network, like 5 and 5. Okay? Now, fully connected, this one is W1, W5. And in principle, if you take a standard feed-forward neural network, this should be W11, W15. If you take shared weights, this guy would have exactly the same weights. So the outputs will be the same everywhere. So it's just one value indeed you're just computing one value. So shared weights does make sense only if you have sparse connectivity. But sparse connectivity does make sense when there is some kind of spatial information here. You know which samples to take together, which input neurons to grab together. And in convolutional neural networks, you know, because there is the spatial dimension of the input, which you want to analyze only a few portions of the image jointly. Okay? Any other question? Okay. These, were good questions. It's important for you to really understand how this machinery works, and not just take as a black box tools in Python. Okay? Now, let's move to another very important aspect in the convolutional neural network, which is the receptive field. So now, there is sparse connectivity. Okay? So we know that this output is only being influenced by a small portion of the input. And this is called the receptive field for this pixel. Now, if you stack multiple layers, what happens to your receptive field, say with respect to the input? So if now I'm stacking like another convolutional layer, 3 by 3, what happens to, you get another output. If I take this sample here, how many pixels in the input are contributing to define this activation? There are 9 here in the input, but in the input image, if I'm taking this value as well, let's take it as a square, in the input image, this means that I'm taking also these other guys. Right? So in this value, in this feature, in this activation, I have also this other guy here contributing. And the deeper you go, the larger the receptive field. So when you get at the bottom of the network, or at the top of the network, they call the top of the network, at the end, say, close to the fully connected layer at the end, the receptive field might be rather large. So one value that you have here when you stack it as a vector, this one might take a rather relevant portion of the input image. Okay? So in a fully connected neural network, the receptive field, it's of course the whole input, because each output neuron takes as input the whole input layer. Since this is not the case in fully convolutional neural network, we got a receptive field that is limited. But that can increase, as you can see, this has to be seen as a one-dimensional convolutional neural network. Okay? Like you are performing convolution of a filter which is 3 rows and 1 column. No, the other way around, 3 columns and 1 row. You can see that the number of pixels contributing to this output is actually the whole input. So let's make an exercise. So I take this network on the top, and I take a pixel here. Okay? So what is the convolution, what is the receptive field of this pixel in the input image? Here, 13 times 15. 15 times 15. Okay, let's see why. So here, if you go back here, is 3 by 3, right? Now, please. 13, okay. 13 by 13. Now, this is 3 by 3. Now, if I go back, 1 pixel is added, right, according to this mechanism. So 1 pixel here is 3 by 3, 9, 3 by 3. And then there is this pixel, includes this pixel, which comes from a 3 by 3. So you see, I'm adding 1 row, 1 column. And the same for this, so it becomes 5 by 5. Then here it becomes 7 by 7, 9 by 9, 11 by 11, 13 by 13. So it should be 15 by 15. No, 13 by 13. So I was wrong. Why? 3, 5, 1 value here. It's 3 by 3, 5 by 5, 7 by 7, 9 by 9. Why? How did you compute the 13 by 13? Yeah, so 5 by 5. So I missed the one number, 7 by 7, 9 by 9, 11 by 11, 13 by 13. So I'm missing something. There. Sorry? So let's try to do let's do the calculation here where there is the max pooling, and let's double check. So here there is a max pooling. So what is the receptive field here? So here, due to the max pooling, is going to be 2 by 2, right? Okay? Because the max pooling actually, one value which is being saved after the max pooling, if the max pooling is 2 by 2, it refers to an input which is 2 by 2. Then there is a convolution of 3 by 3, and this means that here the size was 5 by 5. Sorry, 4 by 4. 2 by 2. Actually, yeah, I think this is simply translated. I think should be shifted there. Because due to the max pooling here, it is 2 by 2. Okay. And here, before the 2 by 2, if you were computing a convolution that was 3 by 3, the output should be 5 by 5, 4 by 4. Why didn't I place the number here? Let me double check. So the convolution is 3 by 3. So each of these, one goes to a 2 by 2, and each of these refers to you overlap a 3 by 3 filter over these, okay? And so the same here and the same here. So it's gonna be 5 by 5, correct? Oh, 4 by 4, you're right. So here it's 4 by 4. Then to the max pooling is gonna be 8 by 8. So to this max pooling is gonna be 2 by 2. Before of this convolution is gonna be 4 by 4. Before this max pooling is going to be 8 by 8. Before this convolution is going to be 10 by 10, correct? Because of this max pooling is going to be 20 by 20, and because of this convolution, 22 by 22. Here we got it. So simply I was writing the number in the wrong location. But here, so what you can see is that convolution increases by adding a certain number of rows, max pooling by doubling the convolutional layer. Sorry, the receptive field. So as you move deeper in the convolutional network, so as you go further down here, you have that the receptive field increases, and the larger the convolutional filters, and the larger the number of layers, the larger the number of the more max pooling you put, the larger the receptive field it will become. Okay? And while you stay in the shallow part of the network, the receptive field is small. So what you can get out of the first filter as output of the first filter, we will see at the end of the lecture or tomorrow, we will see some visualization of what is being learned by convolutional neural network. You got very small patterns. So this is a rather standard figure. What you see is that in order to recognize that this is a cat, the first layer will extract like low-level features that are very localized because they refer to a small portion of the image. Then the receptive field increases, and also the relevance of the exact location of that pattern in the image, the original image, kind of dissolves because the receptive field becomes larger. You can take more, and then it's less relevant where exactly it was inside that receptive field. So in this case, you can extract like more high-level pattern, okay? And then you can assemble these at the end. Your feature here, some of these features might, of course you don't know, might provide a very high response when in the input there is a kind of high-level pattern that is meaningful for separating the data set, the training set, into those classes. So you are spotting out, detecting like higher level pattern, and still you are preserving kind of the relative position. You're not preserving the exact position, but you know that if here you got a large number, this means that it should be like an eye in some region, top part of the region, okay? So you are preserving some spatial relation for the outputs, and at the same time, this decreases in relevance to assess your final decision, and you get more high-level part. So for training, is there any question? Sorry. So far, so good. You got the intuition, you got the feeling, right? Now, for training a convolutional neural network, what you're seeing is that a convolutional neural network, it's exactly, I mean, it can be described as a fully connected neural network with sparse connectivity and shared weights. So if you can compute, with the final loss over a training set, you can define the weight to minimize your loss with gradient descent, okay? You can do still, you can train this convolutional neural network as you were doing for a feed-forward neural network, as long as you can compute the gradient, as long as you can perform backpropagation. And now, you can, the only issue is that you have to take into account of the peculiarities of convolutional neural network and the weight sharing and the sparse connectivity. I mean, the sparse connectivity is not a problem. It means that when you write down your linear combination, you are not taking all the weights, you are not taking so many weights, you are taking just fewer weights. Having shared weights means that when you expand your loss with respect to the weights, the same weight will pop out in different terms. But this, I mean, in terms of computing derivatives, it's just a matter of reorganizing them, okay? And still you can do backpropagation. So what really, the only detail missing is just what to do with the max pooling. Because convolutional layer we can derive, dense layers we can compute the derivative, the same for convolutional layers. The ReLU, it's not a problem. I mean, the ReLU is like that function. The derivative, it's kind of straightforward to see that it's 0 and 1. If you want to be picky, if you are a mathematician, the derivative in 0 is not defined, but you can take the subgradient instead of the gradient and arbitrarily set it to any number you want, set it to 0. And in practice, this wouldn't affect your computation, actual computation over the data set, over the training set. The only point is how to compute the derivative out of max pooling layer. And this is rather simple because we want to compute the derivative of this guy with respect to this guy. So this guy is 1, has not contributed to this because it was not the maximum over the region. So the derivative of this guy with respect to this guy is going to be 0. And only where the max was, so here, in the location where the max was, you assess the derivative to be 1. So, I mean, I'm not entering how to do this. I mean, TensorFlow is great because it allows you to compute gradients of each pixel, each point in your network with respect to any other point in the network, and it exposes this to you rather easily. Can't remember whether it is PyTorch or TensorFlow. Maybe it is. I think it's TensorFlow is doing this. But I mean, you should be rather confident that this is doable, in a sense that as long as we define the gradient related to the max pooling, then we are still back to our framework where we can write all our gradients as backpropagation, and then we can define we can perform, say, stochastic gradient descent or whatever or using Adam optimizer over the net, as long as we define a loss associated to our training set. So far, so good? Even from home, everything is clear? Okay. Now, okay, let's try to train your network. So you take some data set, and you want to train your network, and now here is an overview of a few, rather old, because it's from a few years ago, the first convolutional neural networks that were presented in the literature. And now, so like the first 4 years of convolutional neural networks, you can see here the number of operations required, here the accuracy, which is the top 1 accuracy. So how often you get as first output of the network the right class, the correct class, right? And the reference set probably was the ImageNet data set. So these numbers were reported in this. Now, what is interesting is that the AlexNet is something we're going to talk today. Was the first one, like beating all the standards in image classification, and was called AlexNet because the first author was called Alex. And then there has been like a very substantial increase. And what is relevant to see is also the size of these circles. It refers to the number of parameters, overall number of parameters of the network. Okay, and even if I told you that the convolutional neural networks are rather parsimonious, say they don't use so many parameters, in their convolutional part. As a matter of fact, this network had a huge number of parameters. So the AlexNet, which was like kind of one of the least performing one, probably the least performing one, had about like 60 million parameters. And if you take larger networks like VGG, 16 or 19, we are about like 150 million parameters. So this is even an issue when you download this stuff, right? I mean, not an issue nowadays in our fast connection, but still, it's something you have to take into account. You have to load in memory these guys always. Every time you have to perform inference. So training time, then I'll tell you, I mean, this is like 8 years ago, it's kind of a different story. So now, a few years ago, NVIDIA released a laptop that was able to train like AlexNet in a few hours. Okay, and probably if you take like some performance metric of the last GPUs, it's a matter of few hours. At that time, were a matter of days. But you see the number of parameters, and large number of parameters means if you have to fit 60 million parameters, you would expect quite a large training set, right? Not just a, I mean, you cannot cope with the training set of a few hundred images, right? And typically, in many applications, you are not given such a large training set, or at least you're not given such a large training set of annotated images for which you know exactly the label for the classification. Or you don't have annotations like for localization or for segmentation or for detection or whatever. So these deep learning models are very, say, data hungry because they really require a huge amount of training data in order to set all these parameters. And there are two, okay, maybe there are more, but so far we can mention two measure solutions to have this network to work with reasonably small training set of a few hundred or of a few thousands of images, annotated images. And the first one is data augmentation. So data augmentation is very, very simple and very intuitive. So the scenario where I'm presenting this, it refers to a Kaggle competition that there was addressing the problem of studying the population of sea lions in these Aleutian Islands, which are in Alaska. So there the population of sea lion was terribly decreasing, say, over the last 30 years, so decreased of 95% or something like that. So they were surveying with the drones all these shores in order to find out where the sea lions was, and they want to count them and classify them. Count them because they want to know how many there were, but also how many adult males, juveniles, which are probably not well defined, not yet recognizable whether it is male or female, subadult, at least from a drone picture, adult females, and pups. Yes, pups. It's there. Okay? And now you are given a picture like this, a few hundreds of pictures like this, and you need to provide as output the number of adult male, subadult male, female, juveniles, and pups. Okay? For each and every image. And so this might seem kind of, okay, you got plenty, maybe you are given 100 of these images, like 4K by 4K with high resolution. So you're given a lot of training data. Indeed, some population were rather small. So some sea lions were not very very frequent, like adult male, there were not so many. Okay? So if you want to train a classifier to solve this problem, which is counting how many of those sea lions are in each picture, now you can take, like, the simplest solution ever you can think of is you take this picture, you crop a portion of the image, like 90 by 90, and then you try to patch 90 by 90, and then you try to classify this. Okay? And then you classify these as into one of the 5 classes of sea lions, plus an additional class which is background, say no sea lion at all. Okay? And now to train this classifier, you need to take your training samples, which are given in the big image with a few annotations, crop some patches, and then train your classifier as a convolution neural network that classifies this patch. Okay? But as I told you, like subadult males, there were not so many. There were like a few hundred. So yeah, this is an example of predictions of the convolution neural network. That was a student doing the thesis with us a few years ago that wanted to I mean, the competition was over. It was just to understand better these models, right? So, so this adult male was considered a female. So these are the output predictions. This female was okay. Was considered a female with high probability. And the pup, but this was considered a pup. No, an adult male in principle, no, sorry. It was an adult male. So it was not a very, I mean, it was not a award-winning cover classifier. It was rather simple, based on a convolutional neural network, of course. And still here you realize that you need kind of increase the size of your training set when you want to train these models. Because a few hundred images, if you want to train a few hundred of images of the class subadult male, might not be enough to train a classifier which has like a few million parameters, right? And then here, what you do, or what everybody does, in order to train a classifier, is to use data augmentation. So given a single picture, that is like the picture of that sea lion in that position, select, crop it from the original image, you might assume that, I mean, it is not very relevant the position he had. I mean, that sea lion would be a subadult male even if he was in any other position with respect to the input image, right? With respect to the center image. It can be displaced, it can be rotated, it can be scaled, it can be distorted. But each of these input refers to the same label, but it's a different vector, it's a different input. So maybe you are not adding as much variability as having 10 pictures of different sea lions, but still you are getting like 10 samples where to compute your loss. And these 10 samples, of course, are not the same. So you can use data augmentation to balance your training data such that the class proportions becomes almost the same and your classifiers is not, say, steered towards predicting always the majority class and never the minority classes. And you can use it to provide new training samples at each epoch. So typically when you analyze the whole training set, you are taking, in one epoch, you are taking each image once. But with the data augmentation plugged in, you never take the same image twice in different epochs. Because what you do when you are leveraging data augmentation, and this is already done like built in Python classes to be used during training, you load the original image, you perform some kind of augmentation, and you feed it to the network. This allows the network to learn as well, not only the peculiar patterns of sea lions, but also what are the irrelevant variation in the images for defining the class output. Okay, so if you, instead of feeding only the sea lion in that position, you feed also the sea lion in each and every possible rotation, and the network during all its training epochs sees all these different locations, right, or all these variants, then the network might understand that the orientation of the sea lion is not relevant for defining what is the class output, but rather the relevant patterns are other. Typically, you have like a few percentage of performance boost over like AlexNet, you get it. And but I mean, this is useful because it also helps you to kind of prevent overfitting. Say you have just um, a few images of source-of male that are next, always by chance, next to the stones that are bright. I mean, let's say, okay, most of them are there close to a stone that is bright. So if you move a bit the crop such that this sometimes goes out, the classifier learns that maybe that pattern is not relevant. Of course, you always have the bright dot inside that image, the classifier would learn. Of course. So, and this is the other, the other very relevant observation. The way you design augmentation, it's up to you. I mean, you got off-the-shelf procedures that provides you like geometric transformation, like shifts, rotation, affine, perspective distortion, just to see your patch, like to render your patch as it would have been seen from a different view. Shear, which means like you take your patch and instead of having like squared, you move these up, you right, and these other leftward, such that your patch get distorted like this. What to put outside? Typically, you do some padding. The padding options are like here. You can see. You can see there are some like straight lines. You can see next to these, right? And this is because they were like propagating the same value of these stripes are given to the fact that they were padding the output of the image, say after a rotation, by propagating the same value of the pixel along the line. And you can also do some photometric transformation, okay, flip scaling, whatever, like to zoom in, zoom out, up to a certain degree can be included as the criteria is as long as these do not change the class label. I mean, if you take your, if you admit your scaling to be like of a factor, I don't know, 20, then your some adult male will become like a few pixels, like a pup. Then you understand it. I mean, you are confusing the network by doing so, because you are by including augmentation instead of trying to teach the network to learn invariant properties of your images, you are just throwing away relevant information like the size. So you have to carefully design your data augmentation to avoid this loss of information. And the only criteria is that you have to design transformation that preserves the class label. Okay? But on the other hand, this is also one of the few ways you have to control what the network is learning by training examples. So you can define what the network is learning by defining the training samples you feed to the network. And the documentation is a way to control what kind of training samples you give them. So what kind of invariance, for example, you would expect for the network to be to learn to be considered. And here in these slides, you can find how to include the data augmentation. You have to use image data generator, and I mean, a lot of details. Of course, by this very simple transformation, geometry, say, a priori defined transformation, is difficult to include all the possible transformation you might get. So you can see here, for example, juveniles here are always overlapped to each other, right? Okay, the juveniles are like this. And also pups, they are close to the mom sometimes, or, I mean, by changing, by providing some perspective transformation, some rotation of the image, you are not assembling different samples one over the other. You are not changing much the background. So you're not, if all your images are like this, you are not providing much variability in the background over the very same image. Okay? So the superimposition, the change of background, and the variation in the background, or like autofocus or bad exposure might be also present. And to some extent, you can include these. To some extent, you can include these in your training set, as long as you can like manually define this transformation over the image. Okay, and so for example, this is kind of reasonable to have like some saturation of the picture. You can make it something like you can just scale all the pixel values in the input. You can add some blur, you can add noise, and if your specific problem you are addressing requires some specific type of transformation, then you can configure this on your own. Okay? And so, for example, in the wafer case, so the problem we have been addressing with ST microelectronics, we need to classify these patterns. And for example, certain kind of pattern might appear only in specific locations of the wafer, some other might appear everywhere. So depending on the pattern, you can define specific, depending on the label of the input, you can define specific augmentation that are relevant. Like for example, these, of course, you can perform whatever rotation you want, and it wouldn't change the class pattern. But from others, like the grid has to be vertical or horizontal for some reason that engineers can tell you. Then you can design your data augmentation that takes as input the class. We were designing like class augmentation that we were like taking only portion of the scratches in some cases and feeding them to the network, because, I mean, for example, in these that were very rare, this class, you might take only a few of these scratches over the same wafer and get multiple instances. And this is very useful. And so augmentation can be used at training time with the hope to better learn what are the distinctive properties of your input image for the classification to be addressed successfully. But you never, so if you train your image providing also rotated images as input, you would expect the network to be rotation invariant, right? So if I'm feeding all the images along all the possible rotations, you expect your network to be kind of invariant to the rotation to rotation transformation. So given an input sample, if it is given in a certain orientation or in another, the output would be the same. But of course, there are no guarantees for this to happen. So, and in practice, it is never like this. So what you can do is also to leverage augmentation at test time. So instead of feeding the network with a single sample,
Io metto un'altra roba.
Sorry? Instead of feeding the network with a single sample, you can feed for testing, okay? You can feed a batch or a batch containing multiple augmented versions of the same test sample. And you include in this augmentation all the possible transformation which do not change the class. Okay? So you don't know what okay, now you can say, well, now you can argue, I mean, come on, I don't know the class of that sample. You're right. So you have to define at test time, you have to use only a subset of transformation which wouldn't change the class of your input sample. Say, for example, in my case here, if rotations are not good for this sample, I can use rotation for all the others and not for this training time. But at test time, since I don't know what the label is associated to the sample, I can use only all the transformation except rotation, for example. So there is a subset of transformation which I can use at test time. So instead of feeding to the image, to the network, a single image, I feed to the network a batch of augmented versions of the same image. And this is done by including like an augmentation layer in practice. So this is augmentation. So it's not a volume, it's not a slice, okay? And then each of these slices, okay, this is kind of misleading. Even though it is organized then in a batch, you got multiple augmented version, you feed each of these to your CNN, and for each of these, you get a score over each class, or a prediction, right? So you got the prediction 1, the prediction 2, the prediction 3, and the prediction 4. And then you take, say, majority voting out of these, or you aggregate you sum up the prediction over each class, and you take the class having the largest average, the largest score. Okay? So this is exactly like having an ensemble of classifiers where each individual is the classifier itself, and what you change is just the input. And this is indeed in practice can be implemented as using multiple convolutional neural networks that process like simultaneously multiple images, which are augmented version of the same input. Okay? So far, so good? And now I didn't have time to include them. Maybe we'll get back to these. There are like, in data augmentation, there are like, so this is a very relevant problem that can impact significantly your performance. There have been like more recent study on this, like frameworks based on reinforcement learning to learn what is the subset of transformations that allows you to improve at best your classifier, say being completely agnostic for what are the type of transformation to be used in that specific problem. So just by trying a subset of possible transformations, having a feedback on how it is the testing error, and then again setting everything into the procedure. So this is called augment. And then there is also, can't remember the name. I will get back to this next time. Once you have trained your model, okay, you have typically you have multi-class classification problems. So those that are like I was mentioning before are like 1,000 classes classification problem. So you can draw a confusion matrix. 1,000 by 1,000 matrix. In case of sea lion, it's 6 by 6 because we have only 6 classes. And here you have, are you familiar with the confusion matrix? Yes, no. Okay, then it's good to specify. So, I mean, this is not related to convolutional neural network. This is for whatever classifier. So you got a matrix to show your performance, and over the diagonal, so each row and each column refer to a class. One are the true label here, the other are the predicted label. So over the diagonal, what you have is actually the accuracy over that class, so or the recall, the percentage of images, like, so in this case that were like pups, 80% of the pups were correctly classified as pups, okay? While only 9% of the adult females have been classified as all adult females. On the diagonal, there is the recall, the accuracy over each class. Of the diagonal, there is a proportion of misclassified samples. So here you have that 42% of subadult males have been classified as adult males. Okay? Of course, the diagonal, the confusion matrix you dream of is like this, the identity, 100% of each class is correctly classified as 100%, but if it is like this, typically, it means that you have included the label inside the training samples somehow, encoded somehow in the label inside the training samples. In the real world classification problems, I mean, it's very difficult to get to this, it's very rare you get to this, except from like very trivial problems. I think that now, probably not even on the NIST dataset, the one from digits of 32 by 32, not even recent architecture can get to 100% over each, because there are in some cases there is like noise label. Okay, so some label was wrongly assigned or it's ambiguous. Like label ambiguity we were saying at the very beginning of the image. So I mean, don't quit. Don't uninstall Python if you don't get to this. Okay, so even some intermediate results is good. And if the problem is challenging, you can also cope with like more grayish confusion matrix where there is not like a strong diagonal, colored diagonal. If you are facing, so these are like practical information, but I think these are useful also for you. And I mean, when it comes to deep learning, there is the theory which you get from previous architectures and new tricks we will see and new models we will see from now onward. But also, a very relevant problem is, so a very relevant skills are these practical skills, or this expertise you develop by implementing and trying your solution. And like these kind of best practices are both mentioning in this specific field, in this specific domain of deep learning. And for example, if you take a two-class classification problem, so this is another guideline. So when you're taking a two-class classification problem, the network will tell you just one number, which is the probability to belong to one class. And in some cases, like take, for example, fraud detection, you don't want to consider as fraud each and every sample to be reported that is more likely a fraud than a genuine transaction, because you got a few million of transactions every day, and something that is like 52% a fraud and 48% a genuine transaction, maybe it's not worth to be reported to the investigator that then will call the car holder and so on. So typically in these, often in a two-class classification problems, you might choose to tune your method by setting a higher threshold. Like, I want to claim the input sample to belong to that class only if there is like enough confidence from the classifier, enough evidence from the classifier. So like 80% probability, 90%, whatever. So just when you're training your model, then it's good not to look at the classification error over the validation set or the end over the test set. What is better to look at is the AUC, the area under the curve. So for each and every sample, sorry, for each and every value of the threshold, what you get, it's a point that is telling you the number of false positives and true positives. So you wanted to detect frauds. I set a threshold of 80% over the posterior of my classifier. At 80%, I have the number of frauds that has been correctly classified as frauds, the true positive, and the number of genuine transactions that have been considered as frauds, false positives. And this gives you a point in this. Yes, this gives you a point in this plane, false positive and true positive, and then you can draw a curve. Okay? The area under this curve, it's a good indicator of how powerful your model is, disregarding the threshold. So this can be computed without actually drawing the sample, but the meaning is this one. So it's enough to rank the predictions to according to the posterior, and you can get the area. Of course, what you would like to have here, like the dream, is to have like to be here, like to be the whole area to be one. Say to be here, to have a square completely covered by your curve, because this means that you have 0 false positive and 100% true positive. But again, don't uninstall Python if this is not the case. Okay. Now, let me just mention a few popular architecture to conclude, at least the AlexNet or the VGG. So, okay, this we already seen. The LeNet architecture was the first convolutional neural network proposed in '98. It was meant to recognize, the codes over the zip codes, the postal code over the handwritten somewhere for the postal service. And here they introduce the principles that I've been discussing today: shared weights, sparse connectivity, as a solution to design a neural network specifically meant for images. And the convolution here was interpreted. I mean, there were not so many layers, convolutional layers at the beginning. There were like 2 or 3 convolutional layers, and these were considered really as a way of extracting like partial features. And subsampling was done by averaging pooling. Now we get to this paper in 2012, which was the breakthrough in image classification. Geoffrey Hinton got the Turing Award lately, together with Jan LeCun, which is Jan LeCun, this guy. Okay, now he's leading the Facebook AI research. This guy is in Google, also. Of course, they are also professor. And the other one was Benjo, Joshua Benjo, which is some other very relevant name. And I think he was the advisor for somehow of this guy, but I might be wrong. No, I can't remember. So you see, AlexNet, because that was a nice. The first author was giving the name of the network, and this is the illustration you find. So it seems overly complicated, but this is the picture you can find still often to present the standard architectural convolutional neural network. And there are these two kind of, you see, two vertical parts. That is not part of the architecture. That was just because the network, for training purposes, need to be divided over 2 different GPUs. The GPUs were not so powerful at the time. So the image was loaded and divided into 2 GPUs. The first part was, the top part was being processed by one GPU, the second one by the other. But indeed, it is a convolutional neural network that vastly corresponds the convolutional neural network we have seen before with the LaneNet. The same principle. Few convolutional layers, 5 convolutional layers, and then 3 layers of a multi-layer perceptor. They were able to take as input images that were 224 times 224. They say 27, but probably that's a typo in the paper because it should be 24. It has a huge number of parameters, 60 million, as we mentioned before. Only a small fraction, 6%, was devoted to the convolutional layers. Still, most of the parameters, say most of the power of the model was here in the dense layers that were huge. Okay, 2000 2K times 2K, say 4K because 2K per each GPU. So having a fully connected layer of this dimension, it increases a lot the number of parameters. They were using, so the first layer, they were using like 96 filters having dimension 11 by 11. In the architectures coming next, like VGG, which I'm going to talk about this tomorrow, everybody started using smaller weights, and we will see why. What they were using, what they were introducing, I mean, say from 98, the first convolutional neural network, the first more than a proof of concept that might work, till 2020, say 2012, 14 years, in order to get something like winning a competition. That was due to the fact that there was the winter of neural networks, so researchers were not much very interested in that neural networks anymore. And then there was not enough computational power and annotated data sets in order to train these guys. When GPUs came, when there were initiatives like ImageNet project that was providing huge data set of annotated images, then this model became popular. And by these tricks, it was like a pioneering work, this one, to train these networks to work. They started facing different problems, which they solve almost in the same way we solve nowadays. ReLU activation, which is faster than tanh and can reduce the risk of overfitting. Dropout, which means during training, you remove some sample randomly to, again, to reduce overfitting, and max pooling instead of averaging pooling. The model that was winning at the end was an ensemble of 7 models trained with probably different configuration, and this allowed to reduce the training error of 5, say, of 3%. I can't remember, maybe I have in my notes, sorry, how long did it take to train this guy? Because you were asking me that before. No, I don't have it here, but as far as I remember, a few weeks, a few days. Yeah, 5-6 days to train, 1 week. Okay, it was not in the note. Okay, tomorrow we start from here, from networks that has a different, more familiar representation, and we will see why to use this. Any question? Any comment? Everything okay? Okay, tomorrow online, and please ask questions. Okay, if something is not clear. Thank you very much. Bye.